Solve the polynomial equation and find all real solutions. As a reminder, in order to solve a polynomial equation whose degree is higher than 2, the overarching idea is that we set it equal to 0 in factor. The issue here is that this fourth degree polynomial doesn't factor with the traditional methods, so we're going to use some strategies learned from finding the zeros of a polynomial function in order to help us get this one factored. So what we'll do is we'll consider the left-hand side of this polynomial to be a polynomial function that can be graphed. And we'll notice that the zeros of that polynomial function will be the same as the solutions to the original equation. So we set the polynomial equation equal to y so that we can graph it and look at its x-intercepts. But before we do that, let's consider the p over q list, which is an important part of the process for finding good candidates to help us get this function factored. Remember, p is the constant and q is the leading coefficient. So in this case, the factors of p are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. The factors of q are just plus or minus 1, and therefore when we write all the factors of p over 1, we basically just get a duplicate of the p list. So here we're getting a little shortcut that the p list turns out to be the p over q list. Now we're going to cross-reference this list with the graph to come up with good candidates for zeros that'll help us factor that polynomial. So we put our polynomial function into the calculator and then come over to the graph. And based on the graph, it looks like we may only have 2 real zeros. We know that on a fourth degree polynomial function, we can expect to get 4 zeros. But remember, we only get x-intercepts at the zeros that are real. So from what I can see on the graph, it looks like we might only have 2 real zeros, which is a hint that the other 2 zeros are probably imaginary. It looks like x is equal to negative 1 could be a 0, and negative 1 is in the p over q list. It looks like x is equal to positive 2 could be a real 0, and positive 2 is also in the p over q list. So both of these are good candidates. So we're going to begin testing the zeros, and we do that by using synthetic division. We like synthetic division for testing zeros because not only does it confirm the zeros, but it also helps us to begin the factoring process. So we'll start by confirming that x is equal to negative 1 is a 0. If x is equal to negative 1 is a 0, then x plus 1 must be a factor of our polynomial, which means that x plus 1 would divide evenly into the polynomial, which means that we would expect to get a remainder of 0. So let's begin with the synthetic division. We have our backwards L. Into this box goes the 0 of the divisor. The divisor is going to be x plus 1, and the 0 of the divisor is negative 1. Remember, the 0 of the divisor is also the 0 that we're testing. To the right of the box, we're going to put in the coefficients of the dividend, which is also the polynomial that we're trying to factor. So we've got 1, negative 1, 2, negative 4, and 8. We're also being careful to make sure that we're not missing any terms here. A missing term would require a 0 as a placeholder coefficient in synthetic division. We leave a lane of space and draw our horizontal line, and then begin synthetic division by bringing down this first coefficient of 1, multiply on the diagonal, negative 1 comes up under the next coefficient, combine down to get negative 2, multiply on the diagonal, that product comes up here, combine down to get positive 4, multiply on the diagonal, combine down to get negative 8, multiply on the diagonal to get positive 8, and combine down again to see that the remainder is equal to 0, which confirms that x plus 1 does divide evenly into our function, and therefore x plus 1 is a factor of f at x. So now we can pause with the synthetic division and begin factoring our polynomial. So since x plus 1 is a factor of f at x, it can be divided out, and the other factor is going to be the quotient that remains from that synthetic division. Notice this quotient must be a degree 3 polynomial because we started with a degree 4 and divided out a degree 1. That means that a third degree polynomial remains. And these are the coefficients of our third degree polynomial. So that other factor is going to be 1 as the coefficient on x cubed, minus 2 as the coefficient on x squared, 4 as the coefficient on x, and negative 8 is the constant. Remember, the goal is to get this thing completely factored, so you could either see that this actually does factor by grouping and then use grouping to continue the factorization process. But if you didn't notice that, we would need to go back to the P over Q list and find another good candidate to continue our synthetic division process. Let's do that. So back to our P over Q list and the graph, it appears that positive 2 is an x-intercept. Positive 2 is also in the P over Q list. We'll test to see if x is equal to 2 is a 0, which means that x minus 2 would be a factor, and x minus 2 would divide evenly into the original polynomial. If x minus 2 is a factor of the original polynomial, it must also be a factor of this third degree polynomial. Because if f of x factors more, it's because this polynomial factors more. So instead of going back to the beginning, we're going to divide x minus 2 into this quotient. The 0 of the divisor goes into the box. Notice the 0 of the divisor is also the 0 that we're testing. We leave a lane of space for some work, and we continue with our synthetic division. So we bring down the 1 and multiply on the diagonal. Combine down to get 0. Multiply on the diagonal, 2 times 0 is 0. Combine down to get positive 4. Multiply on the diagonal, 2 times positive 4 is positive 8. Combine down and we get another remainder of 0. And every time we get this confirmed 0, we want to pause with the synthetic division and continue factoring the polynomial. So we copy-paste the x plus 1 factor, and we just confirmed that x minus 2 is also a factor of the polynomial. And when we divided the x minus 2 out using synthetic division, the other factor is going to be the quotient that resulted from that division. That quotient must be quadratic or second degree because the dividend was a third degree and we just divided out a linear factor. That tells us that 1 must be a coefficient on the x squared term. 0 is the coefficient on x, so we don't need to write that term, and then plus 4 is the constant. So we're now here in our factoring process, and let's be reminded that with our steps, once we have a quotient that's quadratic, we no longer need the synthetic division. We have plenty of tools to deal with finding the zeros of a quadratic factor. There are two possibilities for dealing with this quadratic. Either it factors on its own using the AC method, or perhaps it's a special case, but if it doesn't factor, we're going to use the quadratic formula in order to find the remaining zeros from that factor. X plus 4 does not factor, and so in order to find the zeros, we're going to plug in 0 for y, which takes us back to essentially the original equation that we were asked to find, but now our polynomial is in its factored form. Then we'll set each of these factors equal to 0 and solve them individually for x. Subtracting 1 from both sides gives us this 0 that we've already confirmed. Adding 2 to both sides gives us the 0x is equal to 2 that we've already confirmed. The remaining two zeros are going to come from this quadratic factor. When we solve this for x, we're going to get x squared is equal to negative 4. We then take the square root of both sides and we put a plus or minus on the constant side. And we'll see here that we get plus or minus the square root of negative 4, which is 2i. So now it's time to clearly state our answer. We would call these values zeros if we were originally asked to find the zeros of a polynomial function, which is set equal to y. But the original problem said to find the solutions to this polynomial equation. So instead of calling them zeros, I'm going to call these solutions. And they are x is equal to negative 1, x is equal to positive 2, and x is equal to plus or minus 2i. Notice that 2 of them were real and 2 of them are imaginary, which confirms our suspicions when we saw this graph. We had 2 real zeros and 2 imaginary zeros.